Hello, this is Marcel Detra from Polariton Technologies, and today I'm here with Yannik Horst from the Institute of Electromagnetic Fields of ETH Zurich. Thank you very much for joining me, Yannik. For several years, Yannik focused on the applications of terahertz communications, and last June at OFC 2021 he presented his post-deadline paper about the transparent optical terahertz optical link transmission enabled by Plasmonics. Now, before we go into the details of your experiment and your quite astonishing results, can you maybe explain where the interest of the community in this technology comes from and where do you see a daily need for it?
So the global internet traffic trend, also in the past but also for the future, shows that there's an increasing demand for higher data rates, especially for wireless applications. And we see that the wireless and the optical, they need to coexist in the same system. However, nowadays there's a capacity mismatch between the wireless and the optical, and therefore there's a huge opportunity now for the wireless to match to the capacity of the optical. And there's now a trend in research towards higher radio frequencies, or terahertz frequencies, which would then allow bandwidths in the order of optical bandwidths and to overcome this capacity mismatch. And this would lead then finally to applications where we can bridge fiber optical networks or with wireless links or even do beam steering applications.
Well, you could also just stay in the optical domain. I mean, there's also some research happening there.
Yes, but data communications links in general need a higher reliability, and therefore short outage times could have a high penalty for the total link, and therefore terahertz links, they have much more robustness in terms of visibility limited weather conditions such as fog, haze or snow, and also free space optical links had quite a challenge in the last decades or years in corresponding to atmospheric turbulences, and here the terahertz link or terahertz-based links could have a huge potential, so they coexist in the same system and are used for the corresponding applications.
So with your knowledge, could you maybe give us some background of what happened so far in research?
Yes, so in terms of terahertz links, there were already quite some successful transmission links where they were able to show line rates equal or higher than 100 gigabits per second and achieving distances up to 110 meters. And in all of these successful schemes, they used the unitraveling carrier photodiode to heterodyne mix the optical signal to the terahertz domain, so a fully photonic based approach. And on the receiver side, most of them relied on electrical mixers such as Schottky barrier diodes or subharmonic mixers, and these have the benefit of showing high sensitivity. However, they map directly down the terahertz signal to baseband. And if we think back now to future networks, what we discussed before, we want to go back to the optical domain, and therefore how could we do better? One alternative would be to use electro-optical modulators to directly map the terahertz signal back to the optical domain.
Now with this alternative direct mapping approach, what are the advantages, what are the disadvantages?
So one advantage is we don't need any subsequent amplification or conversion steps. So we don't need to go from terahertz to baseband to optical as we would have to do with the electrical mixers. And all this simplifies highly our architecture. In general, electro-optical modulators are broadband and tunable. And also if we go now to the silicon photonics platform, they are at low cost and also very power efficient.
Now let's maybe jump to your experiments, to your setup. On the transmitter side, you used the well-known reliable photonic approach using heterodyne mixing with a UTC. Can you maybe go into more detail on the receiver side and what new approaches you use there?
So what is the challenge now with electro-optical modulators is that the modulators, they need to operate at terahertz frequencies, so have bandwidths that are high bandwidths. And therefore, we use plasmonic modulators, which showed in the past very flat bandwidth or frequency response over 500 gigahertz and also very high modulation efficiencies. And we take this plasmonic modulator, we take an off-the-shelf horn antenna and a laser diode and build our terahertz receiver out of this.
And with this setup and this approach for the receiver side, you actually managed to get some world record-breaking results. Can you also tell us something about this?
Yes, so we started in a 5 meter, so short-range application scenario where we were able to demonstrate 240 gigabits per second line rate at a net rate of 200 gigabits per second. And by using Nyquist frequency division multiplexing, we could overcome the frequency varying behavior of our terahertz transmitter. And furthermore, this was able without any additional amplification on the terahertz receiver side. So the modulation efficiency of the plasmonic modulator was high enough that we could achieve this high single channel data rates.
Now, besides these 5 meters that you managed to get, which is very nice for some short reach applications, you also managed to overcome 115 meters. What were the challenges there?
So in general, if you go to higher distances, especially in the RF or terahertz frequency domain, the free space losses increases quadratically for both of these parameters. And therefore, we had to adapt a bit the antenna design. So we exchanged the horn lens configuration from the 5 meter to a parabolic mirror approach with a high gain for the 150 meters. And with this, we were able to achieve 150 gigabits line rate without any electrical amplification. And then we were interested in if we can further increase the data rate by having a second amplification stage at the receiver. And we saw that we could increase our line rate up to 190 gigabits per second. However, at the cost that the total bandwidth of our system was further limited by the second amplifiers. And therefore, we think in the future we would like to go back to the driverless approach where we have more bandwidth available and find different solutions to go to even higher distances or higher data rates.
Now you just mentioned the future. Could you maybe give us a quick outlook of what this plasmonic modulator technology could lead to?
Yes, so in general, these modulators have a very low footprint in the order of micrometer range. And a former PhD colleague of mine, Yannik, he introduced a novel approach by seamlessly integrating these plasmonic modulators with an on-chip planar antenna. And this has the benefit of even further decreasing the footprint of the terahertz receiver. And also by using resonant antennas, we can achieve high field enhancement and therefore modulation efficiencies that can be used then for communication applications. But also alternatively, this approach can be used for terahertz sensing applications in the future.
Well, Yannik, thank you very much for your time and for sharing your insights.